which means we can jump into chapter 18. Yep. All right. If you're looking for the documents I would have handed out today, this is the chapter 18 electrochemistry PowerPoints. And then the review document is version 2. And of course, the work problems to go along with it. And then, last but not least, the crossword puzzle. Okay. Well, let's see. Let me share PowerPoints. Go. And come on. There we go. Yeah. All right. This is the last topic in the first semester of chemistry. And electrochemistry. Very simply, it just we're going to look at the conversion of chemical to electrical energy, or vice versa, electrical energy to chemical energy. That's the whole purpose of electrochemistry. But we need to define some terms, right? And actually, let's see, do I have my, there it is. Okay, there's a mnemonic device for remembering what oxidation and reduction are, right? Oxidation is loss. So what does that mean? That means is loss of electrons, one or more. So anything that loses an electron in a chemical reaction is said to be oxidized. And then that electron doesn't sit out here by itself. Electrons are like hydrogen ions. They're always transferred from one place to another. They don't sit out here all by themselves. That's physics. If you do that, then you get static charge, and we don't do that in chemistry, not intentionally. So reduction is gain. And let's capitalize that. It's gain of electrons. And they always occur together. If something is oxidized in a chemical reaction, something else must be reduced by the same number of electrons total. You could have individual atoms that are reduced by 1 electron and the other species oxidized by 2 or more electrons. But in balancing the equation, you got the same number of electrons leaving the oxidized species, ending up on the reduced species. Also, if something is oxidized, not Q, if something is oxidized, that equals a reducing agent. Right? Because whenever something is oxidized, it has to send its electrons somewhere. So it causes the reduction of something else. And anything that is reduced naturally is an oxidizing agent. Okay. All right. Now, in order to track the movement of electrons, because we have to do that, if we don't know where the electrons are starting, where they're ending, and how many are moving, then what's the point? So we have some rules that we use. And this is, by the way, this is a bookkeeping scheme. When we talk about oxidation states, this is a bookkeeping scheme that helps us track electrons. We can't say for sure that this is actually what happens, but it does help us understand the movement of electrons. So, rule number one. The easiest one. Let's take an example. Let's say we have hydrogen gas and oxygen gas combined to make water. Okay? So we know we're going to need two of these and two of those. We've done that before dozens of times. The oxidation state of an atom in its most stable element form is 0. So this hydrogen, each one of these hydrogens has an oxidation state of 0. And so does that oxygen. So each one of those oxygen atoms is oxidation state 0. If we have a monatomic ion involved, for instance, if we have sodium and chlorine gas reacting to make sodium chloride, solid. Let's see, we need two of these and two of these. These elements are going to be 0. But we've made an ionic solid over here, which means we know that that's +1 and that's a -1. That is the oxidation state of each element in this compound. +1, -1. Now, they have a full charge. So the oxidation state in this case is equal to the charge. But it doesn't have to be. In compounds, yes, it is. There's Olivia. All right. Come join us. All right. Next. When oxygen is in a covalent compound, right? If we don't know that oxygen is an ion, and a case where oxygen would be an ion would be like this, say sodium oxide, right? That would be a +1 and this would be a -2. That's easy because we know these are ions. But if oxygen is in a covalent compound, it doesn't have a charge. So we have to assign an oxidation state to it. And the reason we're doing this is because we want to be able to calculate the oxidation state of other elements that tend to have multiple possibilities. So we fix oxygen at -2, say in water. That's a covalent compound, and its oxidation state is -2. Okay? That means hydrogen has to be a +1. Right? Now, there's one exception. When you have a peroxide, and the first example there is the peroxide ion, but any peroxide where you have two oxygens connected like that, and then you have some group, it doesn't matter what it is, as long as it's covalent, then both of these together, the oxidation state is -2. So that means each one is a -1. All right. Next, anytime hydrogen is in a covalent compound, then it will be a +1. right? And it usually comes first. Well, not always, but let's say, for example, let's say we have acetic acid, right? Each one of these hydrogens is oxidation state +1. All right. The exception is when hydrogen is bound to a metal. So if we bind, let's say we have magnesium hydride. That has to be a -1 because magnesium is +2. And that's an ionic compound. All right, we're going to get to magnesium and its neighbors in just a minute. Fluorine is always -1, no matter what compound it's in. If we have hydrogen fluoride, or we have sodium fluoride, or whatever, it's a -1. Always. No exceptions. Let me see. Yeah, we're going to get to them. Sorry. The sum of the oxidation states of a neutral compound must be 0. We can't have any unbalanced charges. So that's why for water, the sum here is 2 times +1 is +2, and a -2, and that's 0. So neutral compounds, the oxidation states must add up to 0. If, on the other hand, we have polyatomic ion, like, well, let's take a really simple one, like hydroxide, right? This is going to be a +1. This is going to be a -2. So a -2 and a +1 is a -1. The sum of the oxidation states has to add up to the charge on the polyatomic ion. Alkali metals are always +1. That is the first column in your periodic table, +1. The second column is +2. We learned some of these back in nomenclature, right? Sometimes we paint ourselves into a corner. Right? We have a compound where we don't have a rule. So when chlorine or nitrogen are present with none of the above, right? If any of the ones 1 through 8, if they're present, then they take precedence. We assign the value to them, and then we calculate the others. But if they're not there, then what do? Well, if you have chlorine present, then we call it the same as fluorine. Halogens then would be -1. And then we calculate what phosphorus happens to be. In this case, phosphorus would be +5. In the case where we have carbon and nitrogen, we take nitrogen as -3 because it's 3 steps to the left, right? Fluorine, oxygen, nitrogen. Nitrogen then would be -3, -1, -2, -3. And then we calculate carbon as +3. Actually, it's no, Cn minus, it would be +2. Right? -3 and +2 is a -1. And usually, if we have a case like this, then we fix the oxidation state for the element on the right. The more electronegative will be the one we assign a value to, and then we calculate the less than electronegative as whatever gives us the proper balance. All right, let's try some examples here. Okay, potassium dichromate. Okay, that's a neutral compound. They have two options here. We know that potassium is +1 because it's an alkali metal. We know that oxygen is a -2. Okay? So if we take the total of potassiums, right, +2, and then 7 times 2 minus is -14, and combine them, we get a -12. So if this compound is going to be neutral in its oxidation states, then chromium must supply a +12 total. That means each one of the chromiums must be a +6. All right. The other possibility is we know that potassium is +1. We know that the dichromate ion is a 2 minus, right? So a -2 here makes a -14. And we have to hold two of these out for that charge. So we only balance -12, which is +12 and +6. So either way works. All right. Now we get a polyatomic ion. We did a polyatomic ion right there with the dichromate. But let's see if we can do carbonate. Right? Okay. We have a rule for oxygen. -2 times 3 is a -6. We have to hold two of the minuses out for this charge. So we really only have to balance the -4. That means +4 with a carbon. How about manganese dioxide? Actually, manganese 4 oxide is a proper name. Right? Manganese 4. Oops. Let's get it straight, Dave. Oxide. This is a -2, so that's a -4 total. That makes this a +4. And there you go. PCl5, we did that one earlier as an example of what do you do when you don't have a rule? Well, you have to extend the rule for the halogens in this case. -1, which is -5, and this is a +5. SF4, all right, we have a rule for this one. Right, -1 there, that means this is a +4. Okay, practice, practice, practice. Get comfortable doing this because you need to be able to calculate the oxidation states for all the atoms in a chemical reaction so that you can track the movement of electrons. And we're going to do some examples, of course. In fact, we're going to jump right into a technique for balancing chemical reactions using oxidation states. So before we do that, let's take this balanced equation, right? And then manganate ion. And then iron 2+ ion yields manganese 2+ and 5 iron 3+, and then 4 waters. Right? Now, the first thing you notice about this equation is we left out the counter ions, cations and anions that would balance. Right? What would this one take? Well, say 1 potassium would do that one. Right? It would be, and these are spectators. We leave the spectators out because they just get in the way. And they're not part of, they don't undergo any type of change. Iron. How would you get iron 2+ in solution? Well, maybe nitrate, would be a good choice. But if this is balanced, then let's assign oxidation states, right? There's a charge, right? +1. This is a -2, right? -8 total means -7 is all we have to balance. So this is a +7. There's a +2, there's a +2, there's a +3, and this is a -2 and a +1. Okay? So, which species is oxidized and which is reduced? The one that loses electrons in the when it crosses the arrow. Right? So hydrogen didn't change. Manganese did change. But how did it get from +7 to +2? Remember, you can't mess with the protons, the positive charges. The only thing you do is move electrons. So to get from +7 to +2, we had to gain 5 electrons. So from here to here was a gain of 5 electrons per manganese. And we only got 1 manganese equals 5 electrons total. So that means something else had to be oxidized. This is reduced. Oxidized +2 to +3. So that iron lost 1 electron. Lost 1 electron per iron times 5 equals 5 electrons lost. Right? So this was oxidized. This one was reduced. Okay. And what we've done in this slide is to separate those two into separate steps, a reduction step and an oxidation step. So the reduction step, how do we know? This is obvious, going from MnO4 to Mn2 plus. But how do we know to include hydrogen on this side and water on that side? That's because we're balancing the elements too. We have 4 oxygens here. We got to have 4 oxygens on that side. So we do it with water. 4 waters, but that gives us 8 hydrogens. So we put the 8 hydrogens over here to balance. And the hydrogens are added as hydrogen ions. Now, this is for convenience. We know from our study of acids and bases that hydrogen ions do not exist independent of anything else. But for calculation purposes, for balancing the equation, this works just fine. Okay, so we separate these two into reduction and oxidation steps. And that's why 8 hydrogens plus a manganate plus 5 electrons, right? Reduced, gain 5 electrons. So the 5 electrons go in as a reactant for the reduction. Then oxidation is your 5 iron 2 pluses equals or yields 5 iron 3 pluses plus the 5 electrons that it lost. The lost electrons go on the product side. These are known as half reactions. Now, this was for a balanced equation. We're going to learn how to use half reactions to balance the equation. That's coming up. So what you do is you write if you're given, say we want to take MnO4 minus and Fe2 plus, and we don't have any coefficients, yield manganese and iron 3 plus. That's all we're given. So we put them up there as this. We say MnO4 minus plus Fe2 plus yields Mn2 plus Fe, excuse me, plus Fe3 plus. That's all we're given. So first thing you do then is you determine the oxidation states for each one. That's given, that's given, that's given. This one we calculated as +7. And then you separate them out as reduction and oxidation steps. So we would say for the reduction step, MnO4 minus yields Mn2 plus. And for the oxidation step, we would say Fe2 plus yields Fe3 plus. Okay? Then we proceed to balance these individually before we recombine them. First thing you do is you balance the elements that are not oxygen and not hydrogen. We got one manganese here, one there. That's good. We got one iron here, one iron here. That's good. Then we balance the oxygens with water. So we have 4 oxygens here. We need 4 waters on this side. Then we balance the hydrogens. So +8 hydrogens, right? 8 hydrogens. Okay. Down here, we don't have to do anything else because we don't have oxygen or hydrogen. Then you balance the electrons, right? We know that this is a reduction step and that we need 5 electrons in as a reactant. And this side, we have 5 electrons as, we have to have 5 electrons here. Well, actually, we would start off with 1 electron, right? But we need 5 electrons. So we put a 5 here, 5 here, and a 5 here. Now that we've got the electrons balanced, we can recombine the equation, right? If necessary, right, and we need to, what we did was we multiplied this entire equation through by 5. If we need to do something to both of them to make the electrons balance, then we do it. We use whole number multiples or fractional multiples. It doesn't matter. As long as we get the right number of electrons, same in both oxidation and reduction steps. Once you get to that point, then you can add them back together. Right, and there are your steps. This is how we balance oxidation, redox equations. That's what we call them. Redox equations. That's how we balance them using the half reaction method in acidic solution. Notice here, hydrogen ions. That means the solution is acidic. All right, here's an example. Another example. All right, we're going to separate this equation into half reactions. So we have the reduction step and we have the oxidation step. Okay, what's the reduction step? Well, we have to do the oxidation states first, right? All right. Let's do this. Move that down a little bit. And let's put the raw equation up here. Plus SO3 2 minus sulfite ion. And then we get to chromium 3 plus and SO4 2 minus. Okay. 2 minus times 7 is minus 14. We hold out 2 for that minus. That means we have a +6 here. This is a -2 times 6 times 3 is -6. We hold out 2 for that negative. That means -4 is balanced over here with +4. Chromium's got its charge. -2 times 4 is -8. Hold out 2 for that one. We have a +6 here. Okay, now we can tell which one's which. The reduction step is the one where the oxidation number decreased. It became less positive or more negative. Right? Less positive. This one yields this one. Okay, so that leaves SO3 2 minus with a +4 goes to SO4 2 minus with a +6. Okay, so we got our two half reactions separated. Now what we want to do is balance the oxygen atoms. Right? They both have oxygen, so we want 7 oxygens on this side. There we go. That means we have 14 hydrogens that have to be placed on this side. Okay. We have 1 extra oxygen that we need on this side. And then we have 2 hydrogens to balance those two. Okay. Now we can do electrons. Oxygen atoms, hydrogen atoms. And let's see. Electrons. All right, we're going from +6 to 3+. Right? For each chromium, we need to add 3 electrons. Right? But we got 2 chromiums here. Well, I forgot to do one. This should have been first. I should have done that first. That means we need twice as many. 6 electrons. Right? So for this one, we have how many? We're going from +4 to a +6. We have, wrong side. We have 2 electrons there. Okay? Now, how do we balance the electrons? We need to multiply this whole equation through by 3. 3 times 2 is 6. Right? So this puts a 3 here, a 6 here, and a 3 there, and a 6 here. Okay? Now that we have the electrons balanced, 6 and 6, we can add the equations back together again. Right? So let's try to keep them in this same order. Right? We have 1 Cr2O7 2 minus, and then we have 3 SO3 2 minus. Then we have the electrons cancel. 14 hydrogens plus 3 water. Okay, then on this side we have 2 chromiums, 3 plus, and we have 3 SO4 2 minus. Then we have waters. Let's see, hydrogens first. We have 6 hydrogens and 7 waters. Okay. Now we cancel common terms. Right, we have 14 hydrogens here and 6 there. Those 6 go out, and this becomes 8. And waters, we have 3 waters on this side and 7 on that side. These 3 go out, and this becomes 4. So there's our balanced equation in acidic solution. Before we do that, what if you were given this reaction and you were told to balance it in basic solution? Then we use what I call fake acid balancing technique. You balance it acid first, then you neutralize the acid with hydroxyls. So in this case, we would have to add plus 8 hydroxyls, right, which would yield 8 water. But we have to put 8 hydroxyls on this side too. Right? Okay, so we got rid of this part. With 8 waters here and 4 waters there, now these 4 waters go away, and this becomes 4 waters with 8 hydroxyls on that side. Now it's balanced in basic solution. You got to remember that at this point, all of this is happening in the same medium. Right? So we've got hydrogen ions on this side for acidic solution, but it's all together. So in basic solution, now we got hydroxyls in there, that's all together. The entire solution is basic. Whereas this one, the entire solution is acidic. That's what I call the fake acid method. Now, theoretically, you could balance it. You go straight to the base. But it's a lot easier, I think, if you do the acid first and then convert it to base. All right. Let's see. We got another example here. How we do time? Oh, we got lab. Well, I can bleed over into lab time today. All right. Let's see. In acidic solution. Oh, there's Matthew. I forgot to admit him. Sorry, Matthew. I just now saw you. All right. So in this example, we have bromide ion, the manganate ion. Add those together and you get bromine liquid and manganese 2 plus. All right. Let's see if the animations will take us there easy enough. Nope. It's going to make me work for it. All right. Bromine minus. And I'm going to leave out the states. You normally include the states, but we're just worried about balancing the equation right now. And this takes up less room. Okay, so that's the easy one. Oxidation state 0, because it's element in its most stable form. That's a -1, that's a 2 plus. We only have to calculate this one. So oxygen is a -2, -8 total. We hold one of them out for that minus. That makes this one +7. All right. Now we can separate into the oxidation step and the reduction step. Okay, if we go from a -1 to a 0, how did we get there? We had to lose an electron. Lose an electron means oxidation. Okay. That means the manganate ion goes to manganese 2 plus. All right. So the next thing we want to do is balance the non-hydrogen, non-oxygens. Right. We need 2 bromines. Okay. We got 1 manganese. That's good. Okay. Now we balance the oxygens. Right. No oxygens here, but we do have 4 here. So we have to add 4 waters. That means 8 hydrogens on this side. There we go. Now, how about electrons? If we go from a +7 to a 2 plus, that means we had to gain 5 electrons for each manganese. Right? 5 minuses and a +7 is a 2 plus. Okay? On this side, we had to lose 1 electron for each bromine, but there are 2 bromines. So we actually lost 2 electrons. Okay? All right. Let me scooch this one over just a little bit. All right. How do you get 5 and 2 to balance? Cross multiply. Take that 5 down here. Take that 2 up here. Okay? That means this is 16. This is 2. This is 10. This is 8, and that's 2. 5 times this one is 10. 5 and 10. So now the electrons are balanced, and we can add everything together. Let's go. All right, let's start here. 10 bromide ions plus 2 manganate ions. And then we have, let's see, 16 hydrogens. Okay, got that, got that, got that. That's good. Now on this side, we have 5 bromine, and we have 2 manganese 2 plus, and 8 water. Okay, that's everybody. Okay, do we have any common terms we can cancel? No. Can we reduce it by dividing through by a whole number? No. We're okay until we get to this one, and then we get a fraction. So that's it. That's the balanced equation in acidic solution. Let's see if that agrees. Looks like it does. All right. Basic solution, my fake acid method. Let's make this one basic. So we need to neutralize those with 16 hydroxyls. And that means 16 hydroxyls on this side. Right? So that is 16 waters, 8 waters on that side. So those go out, and these are reduced to 8. So that's your basic reaction environment. And that's all I did. I'm just putting it here in green letters. You balance it acidic, then you convert all the hydrogens to hydroxyls and eliminate the waters. Right, I mentioned earlier that you could possibly balance by going straight to hydroxyls. What if you started by adding hydroxyls first instead of hydrogens? Right? What potential problems could there be? You'll have to add water to the other side to compensate for the oxygen added in OH, then balance both O and H because you added water on one side. So you're just adding complexities. It's much, much easier to do the acid and then convert it to basic. All right, what do we got here? Oh, okay. Balance this in basic solution. All right. All right. Let's put what we got up here. Cn minus MnO4 yields CnO minus and MnO2. Okay. First thing you do, oxidation states. We don't have a rule for this one, so what do? Nitrogen, we assume, is -3. Okay. That means we only have to balance 2 of those. That's a +2. We did this one earlier. I think it's +7. Let's be sure. -2 minus A. Yeah, +7. All right. In this case, we have a -2 here. Now what do? Let's see. Did I go through the steps? No, I didn't go through the steps. We're going to have to say this is -3. Right, -3. That means this is -5, but we need to hold one of them out. So we only need to balance a -4 is +4. And that makes sense. When you know about carbon and what oxidation states are available to carbon, carbon is usually restricted to +4 on the positive side down to -4 on the negative side. So that works. Okay, and this one is -2 and this is +4. Okay. All right, now that we have our oxidation states, we need a reduction step and an oxidation step. All right. How about carbon? Yep, carbon went from +2 to +4, which means it was oxidized. It had to lose electrons. So we put it down here. Cn minus, this is a +2. Nitrogen didn't change because we picked it that way. And then it went to CnO minus +4. That means the reduction step should be MnO4 minus with a +7 to MnO2 to a +4. Okay. Now we balance manganese, 1 and 1, carbon, nitrogen. We're good. Now we go to oxygens. We have 2 already on that side, but we need 2 more. Which means we need 4 hydrogens on this side. Okay. Now we got 1 oxygen there. We need 1 on this side. And balance the hydrogens. Like that. Okay. Now we do electrons. Let's see. Yeah, electrons. All right, for the reduction step, we need electrons on this side. Right? How many? We went from +7 to +4. That means we had to add 3 negatives. All right. On this side, we lost 2. There we go. So now we got the same problem as before. 3, how do you reconcile 3 and 2? You cross multiply. So this one's going to be 2 times that, and this is going to be 3 times that. Right? So this is put a 3 here, 3 there, 3 there, 6 there, and a 6 there. And this makes 6 here, 8 here, 2 there, 4 there, and 2 there. Okay. Now we can add them together. Electrons go out because we've set it up that way. Now let's see, Cn minus was 3. Okay. And then 2 MnO4, then waters. Excuse me. MnO4 minus. then plus 3 water, and 8 hydrogens. And on this side, we have 3 CNO minus. Then we have 2 MnO2. Then we have, let's see, we did water next. 4 waters. And hydrogens, 6 hydrogens. Now we'll cancel common ions, or common terms. So we have 3 waters on this side and 4 on that side. These go out, leave us with 1. Then we have hydrogens, 6 on that side. That leaves us with 2. Now this has to be in basic solution, so we got to neutralize these. Plus 2 hydroxyls, plus 2 hydroxyls. Okay? This makes 2 waters. And we got 1 water on this side, so that water goes out, and that becomes 1. And these terms go out also. So when we balance it, we have 3CN minus, 2MnO4 minus, we have 1 water, yep. Then we have 3CNO minus, 2MnO2s, 2 hydroxyls. That's it. So now we're balanced in basic solution. All right. So up to this point, everything's been in one pot, the reaction. When those electrons move, if you've got electrons going from one place to another, there's always, and especially and always if it's spontaneous, then you have the potential for extracting some energy from that movement, right? If the electrons are moving from a higher potential to a lower potential, then you should be able to extract energy from them. And that's the way they move if it's spontaneous, higher potential, lower potential. But if it's all in one mixture, how do you get access to those moving electrons? You don't. You can't. So what we do is we take the half reactions and we put them in separate vessels. And we connect them with a wire that allows electrons to move from one reaction, half reaction, to the other half reaction. And since those electrons are moving externally, we can access their movement to gain energy. And that's what we call a galvanic cell. All right. Now, where does the reaction actually occur? Well, the reactions occur at the electrodes, right? We need to draw a picture. Let's draw a picture. Let's see, we have an example. Yeah, here's an example. So we have these two half reactions in separate vessels, and we have electrodes in there. Sometimes the electrodes participate in the reaction. Sometimes they don't. But the reaction itself always happens, the half reaction for that cell happens at the electrode. And it just makes sense because that's where the electrons are either entering the solution or leaving the solution, at the electrode. So that's where the reaction occurs. Okay. A basic law of physics. If you have an electrical, if you want to move electrons in a circuit, it must be complete. In other words, if you have something like this and you want to move electrons, it ain't going to happen because that's a broken circuit. You have to complete the circuit for electrons to move. So that's why these two half cells must be connected not just by a wire, but by a salt bridge or a porous disk, some way to allow charges to be completed, moving through that circuit. Now, electrons are going to move in the wire. That's the only thing that can move through that wire. But through the salt bridge or the porous disk, we can move ions. Now, if we had, let's propose, how about this problem? Suppose you had these two half reactions. You had an electrode over here, and let's say the electrons are moving this way, just for argument's sake. If we could get those electrons to move from one to the other, then what would happen? Well, you've got this electronic charge moving across. This would become more and more negative, and this would become more and more positive, right? And we don't do that. So we connect them with a salt bridge, and that simply allows charges to move without a wholesale mixture of the two solutions, right? So if this one is starting to become negative, we want to move negative charges this way and positive charges this way to keep things balanced. Now, the more efficient way to do it is with the porous disk. It provides the least amount of electrical resistance, but the salt bridge will work. Now, we call it a salt bridge because we have a salt in it. Sometimes we put potassium chloride in there in agar. I know what agar is. They use it in microbiology all the time. It just keeps things from wholesale mixture, but it allows the ions to move with some resistance. Okay. There are cautions, of course. If you have silver ions in one side, in one of your half cells, say you have, I don't know, let's say silver ions over here, right? And you have potassium chloride in here, what happens? If these chloride ions move out here, you're going to precipitate silver, right? So you don't want that. In that case, you would say something like silver nitrate. Be a better choice. Right, so there are practical problems that have to be overcome also. All right. So if electrons are moving from left to right in this picture, then the electrons have to come from somewhere. So on the left-hand side, the electrons are moving into the electrode and across. So we're adding electrons to the left-hand side, right? That means that something is being oxidized because the electrons are being lost by something. In order to go into that circuit, those electrons have to be lost. So the oxidation step is on the left-hand side, and we call that the anode. Anode. It equals the site of oxidation. And that is always the case. If oxidation is occurring at that site, that's the anode. Then the cathode equals the site of reduction. Okay? Here we go. By convention, the cathode is on the right. That's just to avoid any misunderstanding. in representing our galvanic cell. Sometimes you'll see it written the opposite direction, but that's not the convention. All right, what do we mean by cell potential? Well, if the reaction that we're hosting in these two separate cells is spontaneous, that is, all you have to do is mix them together, electrons move, then the cell potential is how much push is there behind those electrons that are being moved from one side to the other. I think of, cell potential is a push. It's a pressure pushing those electrons from one side to the other. And we measure it in volts. Sometimes we call it electromotive force, something that's pushing those electrons, right? The higher the voltage, stronger the push, right? And everybody knows intuitively what high voltage versus low voltage means, right? 9-volt battery, right? As a kid, didn't you take a 9-volt battery and touch it to your tongue and get a tingle? Right? That's low voltage. Did you accidentally, as a kid, stick your finger in a light socket? Or when we first moved into my house, we had just built it. And in the basement, there were no covers over the light switches. So my son was like, let's see, he was almost 2, or he was just past 2. And he had to touch everything. So he went down to the basement with me, reached up and touched that light switch and shocked the bejesus out of him. He didn't do that again. That's high voltage. The unit of electrical potential is the volt. And the volt means, in other words, the volt is a derived unit. It means 1 volt equals 1 joule of work, right? 1 joule of work for every coulomb of charge transferred, or 1 coulomb. Now, no, you don't know what a coulomb is. It's just a standard unit of measure of charge. How many positive charges, or how many negative charges, it could be either one, is a coulomb. Oh, okay, we got a video here.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay. All right. So we had this set up as correctly as cathode on this side, the site of reduction, and anode on this side, the site of oxidation. All right. In this case, both electrodes participate in the reaction. So in this case, zinc is being oxidized, so it's going into solution as the zinc 2+ ion. That means its mass is decreasing. But on this side, the copper 2+ ions are receiving electrons and being reduced to copper metal, so the mass of this electrode is increasing. All right, how do we measure cell potential? With a device here. There are two possibilities. The cheapest one is called a voltmeter. It just measures the voltage in the circuit. How does it do it? It's a device with a standard resistor in line, and it draws current and measures the current, the movement of electrons through that resistance. And because it knows what the resistance is, it uses Ohm's law. Let's see if I can remember. Right? Uses resistance. Voltage per I is current. Current is amps or coulombs per second. 1 amp is 1 coulomb per second. So if it knows this one is a constant, then if it measures an increase in current through that resistance, this is a direct proportion, remember, quotients give you direct proportion, then it knows that the voltage is increasing and is calibrated to equate an increase in that current to a voltage. Now, theoretically speaking, the maximum potential that can be derived from a cell is one in which there is zero current, right? But you can't measure it that way with a voltmeter because a voltmeter must have some current in order to equate that to a voltage. So a voltmeter cannot measure maximum cell potential. It can get really close, right? But you need another device if you want to be accurate in terms of the maximum cell potential. So that's called a potentiometer. Let's see, let's put this one over here. R equals V over I. So how does a potentiometer work? Well, a potentiometer has a calibrated device in it for voltage. It can deliver voltage in the opposite direction, right? Voltage, opposing voltage. Okay? It knows it's calibrated, right? It's more expensive to do that, but it is calibrated for a certain voltage, and you adjust the voltage until there's no current. So you measure this voltage at no current, zero current, and then the voltage that you measure here, just change the sign because it's working in the opposite direction. That measures the maximum cell potential. Now, you can get voltmeters. Actually, they're multimeters. They do lots of different things. at any hardware store, or Walmart has them. And they're cheap to buy and cheap to operate. You just need to change the battery every now and then. And you can get pretty close to the voltage. Now, if it's a digital voltmeter, and you connect the electrodes in the wrong direction, it'll come up with a negative sign. So you just flip them over and that's positive. Positive voltage implies spontaneous reaction. Now, there's a problem, obviously, is that if you want to know what is the potential for a half reaction, right? Those reactions don't stand alone, right? But you want a way so that you'll know what to expect from a half reaction, so that if you combine it with another half reaction, which way will the electrons move, right? So what we need is a standard potential. And we compare every half reaction to a standard cell. And that cell is the hydrogen cell. Standard reduction potentials. In other words, let's see. Yeah, I can erase this. The standard potentials are always listed as reductions. That means you're going to have some species plus electrons yield something else. What's the voltage you can expect to get out of that against your standard electrode? Your standard hydrogen electrode is always considered 0. So we fix the hydrogen electrode at 0. That means whatever voltage we get from that arrangement is assigned to the half cell, the variable half cell. Now, standard potential means that the solution is at 1 molar and any gases involved are at 1 atmosphere pressure. Right? We compare them to the standard hydrogen electrode. And this table is in your book, at least the version, the edition that I took it from is table 18.1, is somewhere in chapter 18. Right, those are standard conditions. If we have to flip the half reaction and make it an oxidation, you just change the sign on the voltage. That's all it's needed. When you multiply it by an integer, in other words, if you have to say flip one reaction, make it an oxidation so you can add it to a reduction, you change the sign, but you don't change the value, because under standard conditions, this is an intensive property. Voltage is an intensive property. We don't multiply it by any factor. Now, if we want to know whether it's spontaneous as written, the reaction as written, we need a positive electromotive force, a positive voltage. Means it's spontaneous as written. Right. So here is half of the table. The highest voltage against a hydrogen electrode, the highest half reaction voltage is for fluorine to fluoride ions, 2.87 volts. Right. And then it decreases as we go down in the table. And then, of course, it's going to get to 0 when you get to the hydrogen electrode. right? The standard hydrogen electrode gives a zero potential. And notice that if it's written as a half reaction is a reduction, if you flip it around and say half reaction is oxidation, it's still zero, right? So it doesn't matter which way you write the hydrogen. Right? And then it goes all the way down to lithium reduction is a minus 305. So what does that mean? If you look at that lithium, it's a negative voltage. So lithium does not want that electron, which makes sense. Metals love to give up electrons. They don't like to accept electrons. All right. So your book is going to tell you if you want the standard potential for a galvanic cell, you take the cathode standard potential and you subtract the anode standard potential. And that works, right? All you have to do is decide which one's the cathode, which one's the anode, and do the calculation. All right. I've got a more intuitive method. And I think I've got it in here in a slide. Let's see. Okay, so let's say we have iron 3 plus copper. So copper would be the electrode, right? And copper would be oxidized. So it's on the anode side, right? Let's draw a picture. So here's your copper, right? And here's your iron. Well, no, actually not. So let's say this is a platinum electrode because the electrode doesn't participate. Notice we don't have any iron metal there, right? So this can't be, it's not participating. So on this side, the copper is actually being oxidized to copper 2 plus, right? Copper goes to copper 2 plus 2 electrons. This is the anode. So we're going here to copper 2 plus. Okay. On this side, we're going iron 3 plus one electrode, one electron to iron 2 plus. So in this solution, we've got this reaction. So the electrons are coming out here and participating in this reaction at the electrode. Okay, half reactions. I wrote the half reactions here. Right? So the standard potential for this one, written as a reduction, is 0.77 volts. Okay. How about the other one? Well, that's the standard reduction potential, but this is an oxidation. So we change the sign. So the standard on this side, and this is the cathode. The standard on this side would be negative 0.34 volts. Okay. Now, according to that formula, you take the cathode minus the anode. Well, the anode is plus 0.34, subtract it, makes it a minus, right? So we've already got the minus, just add the two together. And if you do that, now to get the balanced equation, of course, we need to make the electrons agree. But as far as the potential goes, you don't even need to know that. Add those two together, and you get 0.43 volts. So the voltage here is 0.43. Yeah, 43 volts, positive. So as written, left to right, oxidation side to reduction side, you get a 0.43 volts under standard conditions. So that means this solution must be 1 molar. This solution must be 1 molar, both at 25 degrees. And since there are no gases, we don't have to worry about those. Now, the balanced equation is important for one reason. You need to know the number of electrons moving. So we have 2 here, 2 there, and 2 there. How many moles of electrons moved in this balanced reaction? 2. 2 moles of electrons moved. We need to know that later because these are standard conditions. What if you have non-standard conditions, right? Usually less concentration. We're going to introduce an equation that was developed by a man whose name's Nernst. And in order to do the calculation, you need the concentrations of these, and so that we can calculate the Q value. And then you also need to know how many electrons, moles of electrons move in order to use that equation. All right. Actual voltage. There we go. Actual voltage is calculated using the Nernst equation. And it takes into account stoichiometry of both. Now, the spontaneous direction is a battery, is a galvanic cell. But if we put a voltage in here, if we say voltage is greater than 0.43, right? We put a battery in here, and we drive the voltage back that direction, right? Then we can make the reaction go backwards. All we have to do is exceed that voltage under these conditions. Okay. Then instead of a galvanic cell, we have an electrolytic cell. We just drive the reaction backwards. And while we're on the topic, then what would we call these? In that case, this would be oxidizing and this would be reducing. So now this would be the anode and this would be the cathode for an electrolytic cell. All right. I'm not sure I want to mess with these slides. They always give me trouble and my students trouble. But we'll try. If they don't help any, then we'll just ignore them. Strongest to weakest oxidizing agent. So when we say oxidizing agent, what do we mean? The one that has the highest reduction potential. Right? The most positive value on that chart for a species will be the reduction potential. All right. So here are the reduction potentials for fluorine, sodium ions, chlorine, and iron 3+. Right. Now, why did we write them that way? Because those are reduction potentials. Now, the species that we're interested in, we want the iron metal, right? So which one is the strongest oxidizing agent? Which one is the most easily reduced? Okay. Iron 3+ to iron is a negative, so it's probably not going to be such a hot item for strongest oxidizing agent. It's not the most easily reduced. It's too negative. But chlorine has a reasonably high value, 1.36 volts. All right. Sodium is another one. It's a negative. Right? So it's not going to be a very good oxidizing agent. It's not very easily reduced. But when we're talking about, that was sodium plus going to sodium. If we go the other direction, then sodium is not being reduced. Right, so let's take a look at each one. Right, this is written in terms of reduction, strongest reduction. Right, so F minus is not likely to happen. Right, why? Because F minus already has an octet of electrons. Right, it doesn't want any more electrons. So it's not going to be a good, F minus is not going to be a good oxidizing agent. It's not easily reduced. Right? So if we go the other direction and we flip sodium plus an electron, does sodium want an electron? No. Metals love to give up electrons. They don't want additional electrons. So it's not going to be a good choice either. Chlorine is a positive 1.36. That should be a reasonably good oxidizing agent because it is easily reduced. And then Fe plus 3 negatives. Iron doesn't want electrons either. So I think probably the chlorine, the dichlorine atom, it would make the best oxidizing agent. And we're trying to sort of qualitatively arrange these in order. So chlorine would be the best oxidizing agent. The least would probably be sodium, sodium metal. Sodium ion, sodium plus ion, yeah, it wants an electron, right? It'll take an electron, right? But it's probably not as good as chlorine. We don't have standard reduction potentials for the others, so that's kind of a guess. Okay. Up to this point, we took we drew a big picture with an anode on the left and a cathode on the right. But to simplify things, and actually to make it easier to print in published articles, is called line notation. So we have a standard way of arranging things in a line notation that can be easily transferred to the picture form if we want. Anodes are always on the left, right? Site of oxidation. Cathodes on the right, site of reduction. And they are separated by a double vertical line. The double vertical line represents a salt bridge or a porous disk. So we would put the double line here, and on this side would be the cathode. On this side would be the anode. Right? And electrons move externally. Right? Electrons would move from here over to here. We don't write that in. We don't put this in, but that's what happens. A single vertical line on either side indicates a phase change. If, say, from solid to liquid, solid to aqueous, or solid to liquid, or goes to liquid from gas, right? If there's a phase change, we put a single vertical line in there. And we try, if at all possible, to write in the concentrations of aqueous solutions. So here's an example. if we have magnesium here as the solid, right, that's a metal, and there's a phase change here between that and the magnesium 2 plus in aqueous solution. So there's our difference in phase right there. Then on this side, we have aluminum 3 plus and aluminum metal on this side. Right? So the electrons are going to flow from this electrode, the magnesium electrode, externally to this side to reduce it. Right? So that means when it comes in this side, it's going to take these ions and make that metal out of it. And on this side, it's going to take that metal and make these ions by sending electrons to the other side. So this is our line notation. Now, we don't know what the concentration is, so it's not written in for this one. There's the anode, there's the cathode. And we're not saying that this is balanced, right? Because 2 electrons were lost here, but 3 electrons were gained here. So if you're going to write the balanced equation, that's an extra step. But the line notation tells you what you need to know. If the electrode does not participate in the reaction, say we have to use a platinum electrode. I used to use platinum electrodes in an experiment. Or if you want to go cheaper, you can use graphite rod. When we make dry cell batteries, you buy on the grocery shelf, right? The C cells, the D cells, the AAAs and the AA's. The electrode in those cells is graphite because it's cheaper. But it needs to be chemically inert. You don't want it any side reactions interfering with the main reaction. All right. Let's take this information, right? Standard reduction potentials for silver +1 to silver and iron 3 plus to iron 2 plus. Those are the standard reduction potentials. Now, which one of those would we have to change the sign in order to get a positive outcome? If we made the first one negative, negative 0.8, that would give us a negative outcome. Right? So we don't want to flip that one. The iron 3 plus to iron 2 plus, we flip that one. And that makes it negative 0.77. Let's see, do I have that one animated on the next page? There we go. That one becomes the cathode, and the iron becomes the anode. Why? Because changing the sign on the iron potential gives us a total that is positive. It's not very big, but it is spontaneous in that direction. And the cathode would be silver. Let's do it like this. All right. We're going to have phase change on this side. The cathode is on the right-hand side. So this electrode is silver. And this is ion, aqueous solution. All right. And then on this side, we have the anode, which is the oxidation. Right? So this one in aqueous solution, there's no phase change here. Sorry. So you don't put a phase in there, you just put a comma. Like that. And this one is oxidized from this one to that one. This one is reduced from this one to that one. All right. So there's the full picture And the voltage here would be, the standard voltage would be 0.03 volts. Actually, the standard potential, we usually don't write that. We say the standard potential is 0.03 volts. Volts is the unit of measure. E is the variable. Notice we didn't include the counter ions. Right? Fe2 plus, Fe3 plus, probably nitrate would be a good choice because you don't want chloride, right? Otherwise, you're going to precipitate your silver. Oh, I forgot the platinum electrode. Wait a minute. Yeah, I'm sorry. I did forget this one. Got to have the electrode in there. My mistake. The reaction still occurs at the electrode. You're going from Fe2 plus to Fe3 plus at the electrode. All right. That's just rehash of everything we've said up to this point. So whereas your book tells you the cell potential is the reduction potential of the cathode minus the reduction potential of the anode. But I say, write them both as reductions and then change the sign on the one that will give you a total of a positive value. I think that's a whole lot easier. And at the same time, what that does is tell you which one is the anode and which one's the cathode. All right. I used a program for creating this one. And this is a standard cell, right? 1 molar in solution, copper ions on one side, silver ions on the other side. Now, in that video we watched earlier, there was a mention of activity. Which one is more active as a metal? The one that's more active as a metal is the one that is the easiest to oxidize. Right? The one that has the lowest reduction potential. So if you're comparing copper and silver, the reduction potential for the reduction potential for silver is 0.8. The reduction potential for copper is 0.34. So the lower the reduction potential, the more active the metal. It wants to give up electrons. All right. So what would happen to the potential if we increase the copper concentration? All right, so look at that diagram. What happens if you increase the copper concentration? Look at the balanced half reaction, right? Copper, right? On this side, the anode says that copper solid is supposed to yield copper 2 plus 2 electrons, right? That's the reaction at the anode. So what happens if you increase this one? Think Le Chatelier. If you increase this one, then the push is going to be back the other direction. So you're not going this way as strongly, and you're reducing the overall cell potential. Right? Because you can't get as much of this into that form, you don't have as many electrons moving through the external circuit. So you decrease the cell potential. So vice versa. If we decrease this value, if we make this solution less than 1 molar, then we should increase the potential, right? Because it wants to shift this way toward equilibrium. That's a good point to make. These cells, if there is a potential, if you can measure a potential between the cells in that voltmeter, you get a potential, that means that we are not at equilibrium. If you're at equilibrium, then the voltage between the cells is 0, right? They're at equilibrium, so there's no push on the electrons. Now, the standard potential is still some value because it's under conditions of 1 molar concentrations for both anode and cathode. And you would expect to calculate a standard potential for that galvanic cell. Right? But if the concentrations are such that you get a 0 voltage, that means that you are at equilibrium. All right. So we mentioned early, what is electrochemistry? It's the study of the exchange of electrical energy for, or chemical energy for electrical energy, or vice versa. So that means when you're talking energy, you can also mention work. Right? Work, force through a distance, or any other equivalent to that value. So cell potential and work have opposite signs. Remember, when we say system and surroundings, right? If the system is working on the surroundings, right, then this is a negative value. If the surroundings are working on the systems, this is a positive value. So if our galvanic cell is doing work on its surroundings, then the value for work must be negative. But if it's doing that, that means the reaction is spontaneous and the voltage is positive, right? So we have to put in a fudge factor, right? If work is going to be negative, then E must be positive. And if voltage, 1 volt equals 1 joule per coulomb, that means, electrical potential is equal to work, right? This is the variable for that unit of measure. Work per unit of charge. That's Q. Q is unit of charge. Now, I know early on we said Q is heat transfer, but in this case, Q is charge. All right. So if work is moving out of the system, doing work on its surroundings, that's the way we want it. If it's spontaneous and we're extracting work from the system, then in order for this to be positive, this must be negative. That's why the negative work equals E times Q, or work equals negative E Q. Now that's the maximum amount. The maximum voltage here gives us the maximum work. And remember, You can only measure the maximum voltage with a potentiometer when you have no current. Right? So that Q value is current. It has to be 0 for this to be maximum. So that's kind of messes with your mind. All right. There it is. This is in volts. This is in joules. And this is in coulombs. Those are the units assigned to each one of these variables. All right. So any real spontaneous process means that some of the energy is wasted. And we learned about that in the last chapter. Right. Some of it is going to be lost to mine's gone blank. Lost to shoot. Some of it's going to be lost to entropy. And some of it's going to be lost simply to efficiency of the process. Right, so those are two possibilities where the actual work that's extracted from you can have a maximum amount extracted if you account for the entropy. But you will also lose some to the efficiency of the process. So the actual work is always less than the calculated maximum, but we got to start somewhere. So we know the maximum, we can calculate the maximum, we know that the actual is going to be less. Okay. So the actual work done is, let's put it over here. The actual work is negative Q times potential. Now, conversion. Since we work in moles of elements and compounds, then we're going to have moles of electrons also in our stoichiometric relationship, in a balanced equation. So what we need is a conversion factor that can take us from here to the balanced equation, or vice versa. And that's called the unit of the Faraday. This is named after Michael Faraday, who did enormous experimental work in electricity. He was an experimental genius. I'll just put it that way. So one Faraday equals the charge on 1 mole of electrons. So it just means that 96,485 coulombs for every 1 mole of electrons. So if you get 1 mole of electrons either collected in a place or transferred through a wire, you transfer 1 mole of electrons from one place to another, that's equal to 96,485 coulombs. Now, the Coulomb, they didn't just pull Coulomb out of thin air. Right? There's a reason for it, and it comes from physics rather than chemistry. So that's why we have to reconcile that difference here with this conversion factor. All right. The change in free energy equals the maximum useful work that can be obtained from a process. Okay, we learned about that in the last chapter, free energy. So the maximum work is any change in free energy. Remember, if it's spontaneous, then the free energy value has to be negative. Right? So this value is also equal to any change in free energy. And since free energy is negative already, then we don't have to change its sign. Now, this is equal to Q, right? And this is equal to moles of electrons, right? So the 1 Faraday unit, if we solve for charge, then we bring this over here, N times F equals Q. If that's the case, then we can substitute NF in here for this Q. So delta G then is equal to negative NF potential. Oh, and this is max. Max work. Max. There's Michael Faraday. He never got a college degree. He attended lectures, but he never earned a college degree. He worked as an assistant for a while, and actually he ended up with his own lab, and he was inducted into the Royal Society because of the contributions he had made to this study of a number of things, actually, not just electrochemistry. Okay. So this maximum cell potential is also related to the free energy difference between reactants and products in a cell. Right? So if we have this arrangement here, and if we're under standard conditions, then we have that little zero up there above the G and above the E, then the galvanic cell will run in the direction that provides the positive E cell value and the negative value for delta G. Okay. So let's leave this for a time. I'll leave those up there on the sideboard. And we know that if we have a calculated E value, whether it is standard or under actual concentration conditions, we can also have 2 half cells that are exactly the same chemistry. We call that a concentration cell. So one cell is going to be much lower in concentration than the other. The cathode cell will be a higher concentration. The anode cell will be a lower concentration. Okay. So what does Le Chatelier say about this reaction? Well, if they were exactly the same concentration, we would be at equilibrium, right? And there would be no potential whatsoever. But if we look at this reaction, let's see, let's say the anode side. The anode side would be an oxidation. So we would have silver solid, and it would be going to silver ion plus electron. Then if we decrease this concentration, it's going to move the equilibrium position toward the right and produce more electrons, right? So more electrons now are flowing into that conductor and going to the reduction side. And on the reduction side, we're taking silver ions and adding those electrons to make silver metal. So as long as the anode side is a lower concentration in solution than the cathode side, you'll get a concentration cell. Now we're gonna talk about this a little more as soon as we learn how to calculate the actual electrical potential for a cell. And that's where we introduce Walter Nernst's work. He worked in those days, scientists had their fingers in lots of pies. So he worked in the area of thermodynamics, which we've covered already in the previous chapter. Physical chemistry, which we haven't touched. Well, actually, we've sort of introduced some concepts of physical chemistry. We're doing electrochemistry now. He was also interested in solid state physics. That was becoming popular in the early 20th century. And he got a Nobel Prize for his work in the heat theorem that led to the third law of thermodynamics. Now, just as a reminder, the third law of thermodynamics simply says that a perfect crystal, 100% pure, perfect crystal at absolute zero has zero entropy. All right, so here's Nernst's equation. He said that actual concentration, the actual cell potential, we begin with the standard potential, and then we subtract this factor, RT and number of moles of electrons moved times the Faraday constant times the natural log of the Q. So we need to know what this is. We can look this one up. R is 8.3145, right? The one with joules in it. That has to be in Kelvin. This is the number of moles moved in the balanced equation. This is a constant. And the Q value is the balanced equation. You write the balanced equation, and then you assign concentrations to the solution mixture and calculate the Q. So the larger the Q, the more negative this value. And what does that mean? Well, if we write the equation like this, and we want it to be spontaneous that way, if we make the product side too big and the Q too large, right, then we get it wanting to move this direction, and that reduces its potential. But if we make the Q very small, then we subtract less of that term from the standard potential, and that makes a larger actual voltage. All right. Now, if you were chemistry majors, we would settle for this, and you would calculate this each time. But for our purposes, most reactions are going to happen in the neighborhood of temperature 25 degrees here, which would be 298 K. The R is a constant, the F is a constant, and then all we would need to do is combine these terms, and we would get a modified equation that's much easier to remember, of 0.0591 over the number of electrons moved, moles of electrons moved. And we also change the log to common logarithms from natural logarithms. And I've got on the side here, I've got a proof you don't have to remember this. This just proves to you that the change from this one to this one is a valid one. And that's part of the combinations here that give us this constant value. As long as the temperature is 25 degrees Celsius, then we can use this formula. And that's the one we will be using. So at 25 degrees C and equilibrium, Q equals K, and voltage is 0, right? That's at equilibrium, right? We've already studied what is the relationship of K and Q. At equilibrium, they're equal, right? If Q is equal to K, then you have an equilibrium situation and there will be no voltage. Right? But we can also use this if we know that this value, let's see, if we know that there's no voltage and we know that that's that, and this is that, and this is 0.0591 over N, and this is log K, right? Then we just move this one over here and change the sign, right? So now it's standard potential equals 0.0591 over N times log of K. And that's a useful equation to keep, right? We'll keep it over here. So if we know the standard potential for a given reaction, then we can calculate the K for that reaction. So for example, we have this reaction where the half reactions are given. And we know that if we set them up, they're both under standard conditions. The first reaction is 0.71 and the second risk is minus 0.5. So which one would you change to make a positive value? The second one. Make the second one, flip that reaction, make the second one a positive, then we get 0.67 volts if the chromium cell is the anode and the sulfur cell is the cathode. So we need a balanced reaction, right? We're going to calculate the standard potential, and then we'll balance the equation. To find out how many electrons move. That's what we're most interested in. After we know which one's the anode, which one's the cathode, calculate the standard potential and how many electrons move, right? We didn't completely balance the equation because we don't have water and we don't have hydrogen ions in there. That would come later if we need them. But what we're interested in is the standard potential plus the number of electrons that move. And it turns out that 2 moles of electrons move. All right, so if 2 moles of electrons have moved, N equals 2, then, and we know that log K would then be standard potential times number of moles divided by 0.0591. Okay. Log K equals 22.6, then K would be 4 times 10 to the 22nd. This is an extremely favorable reaction, spontaneous reaction, according to K. Right? This essentially goes to completion. And this is not unusual for redox reactions. If they're written in the spontaneous direction, then you're going to have very large K values. That's typical. When is E equal to 0? When the cell is at equilibrium. In other words, you have a dead battery. When is E0 equal to 0? In a concentration cell. Right? E0 in a concentration cell is definitely 0 because E0 implies 1 molar concentration for both cells. That means they're equal. And E0 then would be 0. But the actual E value will either be positive or negative depending on how you switch them. All right. So let's see, how are we doing on time? 10:15. Okay. We got 10 more minutes in lecture, and then we can switch over to lab and finish the discussion. So in this exercise, we're going to construct a concentration cell in which one of the cells is 1 molar and the other one is 10 to the minus 4th molar. So which one is the smallest concentration? It has to be the anode, right? Based upon what we learned earlier, right? So the cathode is going to be the reduction cell, and we put a little subscript of C in there so we can tell them apart. So on the cathode side, we're going to go nickel 2 plus 2 electrons yields nickel solid. That's the electrode. Right, so on this side, we're going to be our nickel electrode and then the nickel 2 plus. And the 2 electrons are going to be exiting here. And electrons are moving that direction. So we have another one over here, and we have another nickel electrode here. And nickel ions here. And this one is going to be going nickel to 2 plus oxidized, so electrons are going to move that direction. Okay? Now, how do we calculate the Q value? Well, you need a balanced equation, right? And we've combined the equations so that we have nickel 2 plus on the concentrated side, or the cathode side, plus nickel solid on the anode side, yields nickel metal on the concentrated, on the cathode side, and plus nickel on the nickel 2 plus on the anode side. All right. So the Q value is going to be, right, the solids don't count. Remember that when you calculate an equilibrium constant. So we have nickel 2 plus on the anode side concentration divided by nickel 2 plus on the cathode side, and that is 1 times 10 to the minus 4 divided by 1. All right. So the log of 10 to the minus 4 would be 4, right? That's why we switched to common log so that we could make these easy calculations. So it's 4 times 0.0591 divided by 2, which would give us 0.118 volts. So we would get 118 millivolts from this concentration cell. Okay, another one. Let's see, we have a nickel electrode in 1 molar nickel, 0.023 volts. Then we have a silver electrode under standard concentrations at 0.80 volts. And these are both standard reduction potentials. Okay, let's sketch the cell. All right, here we go. Here we go. Let's go ahead and put in the salt bridge. All right. So we've got silver and nickel electrodes are going to participate in the reaction. So which side's which? Well, which one of these do we need to flip to change the sign and make a positive value? If we flip the silver, it makes it negative. So we flip the nickel. That makes it the anode. So the anode side is going to be the nickel, right? And nickel 2 plus here. Okay, on this side, that means this will be silver, and this will be silver plus cathode. Okay. Showing the direction of electron flow is going to be electrons move in this direction, like that. And the cell potential is going to be, this is, it'd be 0.80 plus 0.23. So this would be the standard potential for this cell, be 1.03 volts. Oh, okay. It didn't tell us to use the line notation, but we can. All right, so we would have phase change here. Let's see, phase change there. We'd have silver over here and silver ions here. And on this side, we would have nickel 2 plus, and we would have nickel electrode there. Solid. Right? Now, concentrations, right? Well, under standard conditions, concentrations are 1 molar. There it is. Let's see if we got it right. Silver on this side. Okay, we're going to use silver nitrate simply because we don't want chloride anywhere in the vicinity. So we have nitrate ions as counter ions. Okay. Now on this side you have 1 of them. On this side you have 2. And sodium nitrate in our salt bridge. Okay. So as these silver ions are deposited here, because they're being reduced, then what ion moves over here to replace those positives? Sodium. Right? What ion moves out here to replace, let's see. Yeah, we're adding positives here, so we need more negatives. So out here, we're going to move nitrates. Okay. Let's see. Oh, those are the same conditions. Yeah, there's our cell potential, right? Okay. All righty. Now we'll talk about some batteries. This is a representation of a lead storage battery. Sometimes we call it lead acid battery. Call it lead acid battery because the electrolyte, which bathes both electrodes, is sulfuric acid. And because the electrodes are solid and the sulfuric acid is common to both, we don't need a salt bridge. One electrode is pure lead. That's the anode. It's going to be oxidized. The lead anode is going to be oxidized to lead 2 sulfate. The cathode is lead 4 oxide, and it's going to be reduced to lead 2 sulfate. All right. There's the overall reaction. The electrons are moving from the lead electrode to the lead 4 oxide electrode. Now, how many electrons are moving? Well, I think there are 2 moles of electrons. So, as the battery is discharging, supplying electricity, external voltage, we're converting both electrodes into lead 2 sulfate. When we recharge the battery, in other words, once your engine starts and the alternator kicks in, it will run that reaction in reverse and convert the lead 2 sulfate on one plate into lead and on the other plate into lead 4 oxide. So when we start the engine, we are using it as a battery, and when the engine is started, we're using it as an electrolytic cell. Okay. How do we get 12 volts out of that cell, out of that battery? Well, it's a rule in physics that if you have a battery with, say, a negative here and a positive here, and you put them in series, positive, negative, and connect them like that, and then we have another one over here. Well, each cell, if you take the half cells of the cathode and the anode, and you apply Nernst equation, then you get 2 volts for each cell. If you connect them in series, then they add together. Right? So far, we've only got 2, 4, 6, 8. We need 2 more. If we had 2 more, then we get 12 volts. And that's a 12-volt battery next to your engine in your car. Now, some engines, like big diesel engines, they need a higher voltage to push that starter motor. So they'll put, instead of 6 cells, they'll put 12 cells in there and make a 24-volt battery. And of course, you have to have the starter has to be able to handle it. Okay, we have other types of galvanic cells. This is the dry cell I was mentioning earlier with the graphite rod. The anode is the liner of the battery, which is made out of zinc. So the zinc is going to be oxidized to zinc 2+. And in the paste, which is why we call it a dry cell, because if you punch a hole in it, nothing comes out. It's not liquid. But it is a solution, right? So technically it's not dry. We have manganese oxide and ammonium chloride, and that carbon electrode is the site where electrons enter to reduce the manganese, I believe. Reduce the manganese from 4+ to probably 2+. But the graphite rod doesn't participate in the reaction. Okay. Another types of battery. This is, sometimes we call them button cells because they're little, they look like buttons. We don't use this chemistry anymore because of the mercury. So these cells are made small so they'll fit in small devices like hearing aids, calculators, but we substitute a different chemistry rather than mercury, but it still works. Here's another, actually, there's a lot of money and time and brain power being put into trying to make this battery type work. We call it a fuel cell. The reason we call it a fuel cell is because as long as you've got hydrogen coming in one side, oxygen coming in the other, it will never run out. You continue to supply reactants. But it is an electrolytic, a galvanic cell. And the only product is water, steam. So these things run very hot. The fuel cells, the first time they were used, well, I don't know about that history, but I know they were used in the space program, right, in the 60s. When our Mercury, Gemini, and Apollo capsules were being built, they had plenty of oxygen, right, because we had to supply oxygen for the astronauts. So they just bled off some of that oxygen, and they had a separate tank with hydrogen in it. And they put these together in the fuel cells and produced all the voltage they needed. Until Apollo 13, when the oxygen tank blew up. Then they were in real deep trouble. That's another story. But these fuel cells run very hot. So they have to be isolated and insulated against all other components in your vehicle, whatever it happens to be, your car, your spaceship. The chemistry and the catalysts used have been improved so the temperatures have come down, but they still run hot. Right? And that makes sense because what type of reaction is it where you have hydrogen gas and oxygen gas making water? In this case, it's hot enough for liquid, right? Where you have two here and two here. That is an exothermic reaction. It gives off a lot of heat. So you've got to have some way to get rid of that heat. All right. These are the types of galvanic cells that are desirable. They produce voltages, electron movements that we can use to do work. But there are some types of galvanic cells we don't like. And those contribute to what we call corrosion. Corrosion is the conversion of a metal into an oxidized form of the metal. Very often that is an oxide of the metal. So the best example of that is where you have iron. The iron, metal, and oxygen gas yielding rust. Now, that's not a balanced equation. Let me see if I can balance it. Let's see, if we have 2 here and 3 here, let's put a 2 there and a 3 there. And then let's put a 4 here. So that's a balanced equation. We don't like this one, right? Electrons are transferred, definitely transferred, because this is 0, this is -2. So this one is being reduced, this one is being oxidized to 3+. We don't like rust. This is what happens on the surface of a iron or stainless steel bar, not a stainless steel, any steel bar. If you get a little water droplet, it sets up a galvanic cell right there on that little droplet. And the anodic area is the one where this one becomes that one. And the cathodic one is where oxygen becomes that, and we produced rust as a product. Okay. Now I might add, when you see a car or a tractor or something sitting out in the field, and it's been out there for several years, if you look closely at it, you'll see the surface flaking away like that. The reason for that is that rust has a much lower density than the steel, the iron underneath. So less density means for the same mass, it expands. So it flakes away from the surface. What that does is it exposes fresh metal underneath, and it just keeps rusting until it's all gone. Eventually, it'll be nothing but a pile of rust. So how do we prevent corrosion? In other words, converting metal into the oxidized form. Well, the simplest way is to coat it with something, right? Paint it. If you paint the metal and you exclude water and oxygen, then you don't get that galvanic cell set up and you don't get the rust, right? That has to be renewed every now and then because weathering will often introduce pinholes, places where oxygen and water can get through. So you have to inspect and paint often. The other way you can do it is to coat the metal, particularly steel buckets. We used to coat those in zinc. Remember, we talked about metal activity. Zinc is more active metal than iron. In other words, zinc has a higher potential for oxidation than does iron. So zinc will oxidize before iron does. And we sacrifice the zinc on the surface so that it forms this zinc oxide. And that's why if you find an old galvanized bucket, it'll have kind of a grayish coat on the outside. That's the zinc oxide. And what it does is it seals the underneath metal from further attack. The other way you can do it is alloy. You can take a metal and add a more active metal to it, and it will do the same thing as galvanizing or coating. The best example of that is stainless steel. Stainless steel is a combination of iron and chromium. So you put those two together, and the original concentration was in the neighborhood of 35% by weight of chromium. So what would happen is, on the surface of the metal, right, you have iron and chromium and iron and chromium. And if you scratch it, chromium is so reactive with oxygen that will instantly seal the scratch. Right? So the chromium will oxidize and seal that scratch, and it's so small, usually, that it still looks shiny, even with a scratch. And the chromium forms a chromium oxide seal on the surface of the metal, and it doesn't rust. Okay. The last possibility is called cathodic protection. So let's see. I think I have a slide on that. Yeah. So here's a buried iron pipe. If you left that iron pipe in the ground, as is, eventually it would rust away. It won't rust as fast as it would on the surface because there's not as much oxygen underneath the ground, but eventually it will. It'll rust away. So we get a more active metal like magnesium and connect the wire between the magnesium electrode to the pipe, the iron. The magnesium becomes the anode. It rusts. Well, it doesn't really rust, it oxidizes. and releases electrons because it's the anode. It sends electrons into that wire. They go to the iron pipe and they maintain the reduced status of the iron in the pipe. That's a sacrificial anode. This happens also with aluminum. If you take an aluminum can, with or without the paint, throw it out, 100 years, it'll still be there. As long as it's not disturbed, it'll remain aluminum, because aluminum is so reactive that it forms aluminum oxide layer on the surface and excludes any further oxidation. And that's one of the reasons that it's so difficult to refine aluminum oxide into aluminum. The bauxite ore is essentially aluminum oxide. And it's difficult. It takes a lot of energy to get it to reduce the aluminum in the aluminum oxide into aluminum metal, because it's so reactive. It takes a lot of energy to break that bond. Okay. So those are the ways that we can prevent corrosion. Now, ocean-going vessels that are exposed, they have steel hulls and they're exposed, they're painted, but they can become exposed over time to salt water, which is even more corrosive than fresh water, because it has dissolved ions that can transfer charge. So what these big ships do is they have a belt in the hull of zinc. And as long as the engines are running and they have generated power, they trickle electrons into that zinc. And it keeps the zinc reduced, and the iron hull is also reduced, so it doesn't rust. If they have to stop for repairs or to offload cargo or to load cargo, then they may have to shut the engines down to do service, for instance. And once they have no more electricity running through the system, that's assuming they have batteries that aren't working either, then you don't get that trickle of electrons into the zinc, and the electrons now oxidize and send their electrons into the iron and keep the hull from rusting. That's called cathodic protection. Also, in your water tanks, your water heaters at home, they have this anode that's sticking down into the solution, made out of aluminum. And it will corrode over time, so that the water doesn't go into your copper pipes and corrode your pipes. All right. Now, that's not a problem for some of the newer houses, because they're starting to use plastic pipes, which I don't like. I prefer copper. But that's just the way it is. All right. So that's a good type of galvanic cell and a bad type of galvanic cell, and what to do about it. Now let's talk about running the reaction in reverse. Force the current through the cell in a reverse direction to the spontaneous direction, and you'll drive the reaction backwards and turn the cathode into an anode and the anode into a cathode. All right. Here's one example. If you have hydrogen and oxygen in a fuel cell, it will spontaneously react and produce electrons that can do work. But if we want to produce hydrogen and oxygen elements, we have to force, by introducing direct current into water, we can force the reaction backwards and produce hydrogen and oxygen as products. This reaction can occur also where we don't want it. Right? Lead acid batteries, if we overcharge them, then we can start to, if the battery is charged as far as it'll go, and we're still putting electricity into it, we can split the water molecule and make hydrogen gas. And if hydrogen gas builds up in your battery and you don't vent it somehow, then it can explode. Right? So that's why every battery in any car has these little pinholes in the caps. That's to let the hydrogen out in case you overcharge it. Now, most modern cars have voltage regulators, and it can sense when your battery is fully charged, and it will stop charging it. And in fact, that type of electronics is required in lithium-ion batteries. Because lithium-ion batteries, if you overcharge them, they will catch fire. So we have an electronic chip built into lithium-ion batteries that tells it when it's fully charged and to stop sending electricity into it. If we electrolyze water, then we can produce hydrogen, right? Hydrogen is a fuel. You can do lots of things with it, right? There are some cars, experimental cars, that run on hydrogen in their internal combustion engines. Or you can run fuel cells with it. And the nice thing about it is the only product of the use of hydrogen is water, right? So you're not adding any carbon to the environment, which makes the environmentalists very happy, right? If they could be happy. I think environmentalists are naturally depressive personalities anyway. But in order to do that, you need a cheap source of energy. And I mean dirt cheap. Solar energy, wind energy, too expensive, right? It will not satisfy. Fossil fuels, they're kind of on the borderline. Nuclear power, if we can go to a nuclear powered economy, then we can produce hydrogen till the cows come home. But there are other factors. You'd have to change the infrastructure, right? We're set up now for using fossil fuels, like oil tankers, gasoline stations, methane pipelines. That might be easier to convert, right? Just change the methane over to hydrogen and send it through the lines. But it would take an infrastructure restructuring in order to make the hydrogen economy work. All right, so the stoichiometry of electrolysis is essentially unit conversion, right? Remember, very early in the semester, I said a lot of chemistry problems are solvable with dimensional analysis. So if we have a situation where you know how much current you're running through in the reverse direction, you know how much time it's running, then you can change that into how much charge, convert that with the Faraday into a number of electrons, then use the stoichiometry of the balanced equation to say moles of analyte, and then convert that to mass. So this is essentially dimensional analysis, right? An amp, right? 1 amp is equal to 1 coulomb per second. Right? So if you have a 1 amp current and you run it for 60 seconds or 1 minute, you're going to get 60 coulombs. And we can convert that into moles of electrons, right? Just, let's see, 96,000 something. What's that value? 96,485. 485 coulombs per 1 mole of electrons. Divide that into this. That's how many moles of electrons moved. And then we can use the moles of electrons in our balanced equation to complete the stoichiometry. Okay, here's a good example. All right. So we have an unknown metal that's electrolyzed. In other words, in the forward direction, we're oxidizing the metal. In the reverse direction, we're reducing it. So it took 52.8 seconds for a current of 2 amps to plate 0.0719 grams of the metal from a solution containing the metal as a nitrate. What is the metal? All right. The question we need to answer is, what's the molecular weight of the metal? Mass per mole. Okay? We got the mass, 0.0719 grams. We just need to know how many moles of metal were deposited. All right? So if you have a current of 2 amps running for 52.8 seconds, we can calculate how many coulombs of charge that equates to. So 2 amps is 2 coulombs per second. All right? And how many seconds was it running? 52.8 seconds. 52.8 seconds. So seconds cancel. Now we're going to convert coulombs to moles of electrons. Right? So 1 mole of electrons is 96. I always forget that value. Come on. 96,485. Coulombs per mole. So now we have that many electrons. Okay, what we need to know now is what's the relationship to moles of electrons to moles of metal. So if we look at it this way, so we have a solution of metal. So what's the charge on the metal? Nitrate is a -1, and you got 3 of them. So this is a +3, right? +3 electrons yields that metal. Okay? So if we have moles of electrons, then what's the ratio? Moles of electrons to moles of metal. Right? It's 3 to 1. Okay? So that's moles of metal right here. That gives us our answer. Well, part of our answer. So let's take 2 times 52.8 divided by 96,485 divided by 3, which is 3.65 times 10 to the -4 moles of metal. 3.65 times 10 to the -4 moles. All right, so I get 0.0719 divided by that value, 197. 197 grams per mole. Okay? Go to the periodic table. Look for 197 as a molar mass. And the nearest thing I can find to that is gold. So we're plating out gold on something. Now, maybe on a silver base or a copper base, who knows? Well, there it is in one slide. And after we went to all that trouble, there it is. Okay. Now, here's another possible use for the standard reduction potential for elements. if we have a solution that's 0.1 molar in each one of these ions, 2+ iron, copper, tin, nickel, and zinc. What's the order in which the metals will plate out as the voltage is turned up from 0? Well, which one will plate first? Right? The one that has the lowest potential, because you're bringing the voltage up from a low level to a higher level. So the first one that's going to plate out is the one that is the most reducible. The metals are going to form at the cathode because we're adding electrons to them. Site of reduction. So we compare the reduction potentials. The more positive the standard reduction potential, oh, I'm sorry, I got it backwards. The more positive standard reduction potential plates first as the voltage is increased. Right, because we're going in, we're going in reverse. I'm sorry, we're going in reverse. So the one that has the highest reduction potential will plate first. So here's our list of reduction potentials. Okay. And there. So they're actually in order already, right? The one with the highest reduction potential will plate first. Oops. Right. So the highest reduction potential means that we need less voltage to reduce the copper to go from positive to, well, actually a positive value. It's very agreeable to that. But the more negative the reduction potential, the higher the voltage has to be to oppose it in the other direction. All right. So how is electrolysis used commercially? Well, production of aluminum is probably the most consequential to our modern society. We've got aluminum everywhere. During the emperorship, during the reign of Napoleon III, aluminum was more expensive to produce than gold. So Napoleon III would serve his dining ware would be made out of aluminum, because that was an expression of his greatness, his power. He could afford to make eating utensils out of aluminum. And we'll talk about that more in just a minute. There was what made it so cheap, right? Why can we wrap our food in aluminum and throw it away now? Because of a development that we'll discuss in a minute. Other ways of using electrolysis is purification of metals. Right? Copper metal, when it comes out of the ground, of course, is an oxide. It's the ore, and it can be reasonably converted into, say, 95% copper metal. But that's not pure enough for electrical conductors. We need 99.999% pure copper. And the way to do that is through electrolysis. Right? You put your copper plates in this solution. You you put the copper in solution, and then you have a plate in here, and you run the reaction in reverse so that the copper will plate out as pure copper on that. And you don't increase the voltage to the point where it will plate out other contaminant metals. You only do the copper. It comes out first. So the voltage has to be adjusted properly. And you get 99.999% pure copper on that plate. Metal plating. We used to have, on our cars, we used to have chrome bumpers. They were made of steel, but we coated them with chrome so they wouldn't rust. And we did it through electrolysis. And antique cars now, you can still go to there are various shops scattered around the country that will chrome plate your bumper. Right? If you have an antique car, then they can refinish the chrome. I used to have a bicycle that was chrome plated frame. We can also produce elements other than aluminum. Now, aluminum is one very substantial consequence of electrolysis of the oxide of aluminum. But you can also electrolyze other compounds. And there's a lot of sodium and chlorine gas made from electrolysis of table salt. And of course, we can make bleach, right, out of chlorine, or you can put it in other organic reactions, or you can have sodium metal, and you can make sodium hydroxide out of that and clean your drains. But it's used for a number of things, not just drain cleaner. All right, here's the process that purified aluminum. It wasn't until the late 1800s that these two 22-year-old students came up with this process of electrolysis for purifying aluminum from its ore. Charles Martin Harle was in America, and he approached the problem from a scientific standpoint. He was a student in college, and he learned about this newfound process of electrolysis. Paul Héroult was a Frenchman, and he was more practical engineer. So he approached it from a different direction, and they arrived at the same conclusion. And they filed patents in their respective countries almost simultaneously. So their names are both attached to the process. The trick is getting the aluminum oxide into molten state, right? Until it's molten, you cannot electrolyze it. You have to get it in the liquid state. And aluminum oxide has an extremely high melting point, over 2,000 degrees. So the solution was to mix some aluminum oxide with cryolite or sodium aluminum fluoride. And that reduced the melting point of that mixture to 960 degrees, which was doable in those days. They could heat it up to that temperature. Then they would stick their graphite rods into that mixture and send electrons into it, right? And that would reduce the aluminum in that solution, and it would sink to the bottom. And then once it had run its course, and this is an engineering problem, once it had run its course, then they turn the things off, they replace the graphite rods, and while they're doing that, somebody comes along and they knock the cap off of the bottom, and out comes the pure aluminum. And they just cast it into these huge bricks and send it to the customers. Now, the one thing that makes this economical is cheap energy. So you're going to find aluminum processing plants wherever they can get cheap energy, right? One of the cheapest forms of energy is hydroelectric, right? Because usually the government builds the dam, and then the electricity is just pennies for every kilowatt. Or you can build a plant in areas where coal is plentiful. right? Coal-fired power plants are reasonably economical. And then all you have to do is get the ore to the plant. So these plants are usually situated on navigable streams and rivers, right? So that's why aluminum now is so cheap. And Charles Martin Hall and Paul Heroult got fabulously wealthy as a consequence of their invention. All right, we can electroplate spoons, right? You can get a base metal spoon and coat it with silver, and it looks fancy, but it's not silver all the way through. Or here's where we take molten sodium chloride and electrolyze it. We get chlorine gas off of the anode, and we get sodium metal off of the cathode. Right. So that's all there is for us to consider in the lecture part. Right? You got review document, and I'm working from version 2 of the review document. And there are various problems in there that you can work on, and by next Monday, we'll come back and do a review for that exam. So that means the exam for this will be 2 weeks from today. Yes. On May 11th, which puts it in the final exam week. So we'll have exam on just this chapter in the final exam week on May 11th.